Okay, in this video we're continuing our discussion for Algebra 2. We're deviating just a little bit from the textbook today, and we're going to take a day or two just to talk about the behavior of exponents, where they come from and how they're going to help us as we move forward in this class. So the agenda for this video is we're going to cover a quick description of what exponents are, how they can be, or how they're derived from repeated addition, a quick description of exponents, and we'll identify components of the exponents. And then finally, when we finish out this video, we'll be doing a couple examples that are derived from the law of exponents. So to begin with here, first off, repeated addition. If we have several of the same values that are being added together over and over again within a problem, we historically have found a shortcut for that, and it's known as multiplication. So as an example number 1 here, if I saw the numbers 5 and they had to be added together a bunch of different times, we might recognize that 5 added together a bunch of times ends up being 5 times 3, and consequently that's the same as 3 times 5, and we're able to very quickly add 3 5s together using multiplication. Of course, we can exaggerate that even further, but let's say that I had 5 and it had it to be added together way more than 3 times. Let's say we were just adding 5 together, I don't know, 150 times. If there were 150, we can abbreviate that here with n equals 150. That's my way of saying that there are 150 of these 5s in a row. I'm not going to sit here and try adding 5 plus 5 over and over again this number of times. We're literally going to take the number 5 and multiply it by 150. And we'll finish with 750 as the result. This multiplication saves us a bunch of time. Well, in the context of Algebra 2, we see things a little bit more complicated than that. Soon we're going to be working with expressions that we call binomials. And I might have something like this, a 3x plus 1, and to that I'll have to add another 3x plus 1 and another 3x plus 1 and so on. Let's say I had 4 of those that had to be added together. Well, instead of combining like terms and collecting all the like terms and distributing and I should say clearing all the parentheses, we could treat this as a multiplication problem. Since it's 3x plus 1 that's being added together 4 times in a row, we can multiply this 3x plus 1 times 4. And we don't often see the number 4 on the right side of this parentheses, but we can move it to the other side. Just like we were saying before, the multiplication of these two numbers could be reversed. That's the commutative property of multiplication. So if it makes you feel a little bit better, we could write it this way: 4 times 3x plus 1. And from here, you might recognize the distributive property over multiplication. And this 4 times 3x turns into 12x, and the 4 times 1 turns into 4. And this multiplication, again, saves us some time. Instead of having to add 3x with 3x 4 times in a row and the 1s with each other 4 times in a row, to avoid all of that extra hassle, we've resorted to multiplication as a quicker way to perform repeated addition. So here again, if multiplication is the result of repeated addition, then we can also say that repeated multiplication can be replaced with what we call integer exponents, or exponents are a way to simplify repeated multiplication. So let's see an example of that. Three multiplied by itself several times in a row. Let's say 5 times in a row. We could sit here and try to multiply 3 times 3 and take that answer and multiply it by 3, and that answer multiplied by 3 again, and so on. But this notion of repeated multiplication comes into play, and we can change this repeated multiplication into an integer exponent, where the base being 3, the base of this exponential expression is 3, it's the number that's being multiplied. 5 ends up being the counter. This exponent becomes the counter It tells us how many of the 3's are multiplied together. This small expression, 3 to the 5th power, accounts for the result of 3 times itself 5 times in a row. And 3 to the 5th ends up becoming the number 243. In a similar case, we could have done a group or a binomial like we saw in example 3 and repeatedly multiplied that together and also report it as an exponent as well. So as far as the components or the parts of an exponent or exponential expression, there are basically 3 parts: the base, the exponent, and the resulting factors, we sometimes call it. So let's take a look at that. Again, as we had mentioned before, the number at the bottom, this full-size number, is what we would call our base of the exponent. And the 5 here is the exponent itself. Some places or some textbooks I've seen it called a counter. This counts how many times we're multiplying the 5 together. And then the result, as it's written in its expanded form, we would say are our factors. So not this here, that's the solution, or that's a simplified result, but I would call these the factors. The factors are the lists of the products necessary that would multiply together to equal the exponential expression. So if I provide another example and state that I'd like to write an exponential expression, or equation in this case, with a base of 2 and an exponent of 5, you would need to know that that's represented by the whole number 2 raised to the 5th power. And when written in terms of its factors, that would look like this: 2 times 2, 5 times in a row. The factored form, if you will, of the exponential expression is shown here. The components that multiply to make this exponential expression are known as the factors. An example that we're going to see in Algebra 2 might look something like this, where we might have a base that's an expression, we'll call it x plus 3, and an exponent, let's just call that 2 for now. This would end up looking like x plus 3 as a group raised to the 2nd power. Now I'm using parentheses here because it's not just the x that gets raised to the 2nd power, and it's not just the 3. If I don't use the grouping symbol, we might mistake this expression to say that the 3 is being raised to the 2nd power but not the x. So by including the grouping symbol, that enforces the fact that the entire group is being raised to the 2nd power. And the factored form, or the factors of this exponential, would look like this: x plus 3 times x plus 3. Now the results to each of these computations can be found, or can be simplified, if you will. 2 to the 5th is equal to the number 32, and x plus 3 to the 2nd power, or x plus 3 squared, is x squared plus 6x plus 9. Now, if you know where this is coming from, that's great. If you're not sure how I got x squared plus 6x plus 9 from this group here, that's okay. Part of what we're doing in this unit for Algebra 2 is being able to transition between both of those answers: the factored form, the simplified form, and the exponential form as well. So in the last part of this video, I want to talk a little bit about the law of exponents. There are a few rules that are associated with the law of exponents. Product, quotient, and power-to-power rule are some of the most common. However, the zero power and the negative power rule are helpful as well. So let's see some examples of that. The power rule would be for something that looks like this. I have some base and an exponent. Let's call it 2. And I have another base that's the same with a different exponent. Let's call it 3. It would be helpful for us to know what the result of x squared times x to the 3rd power ends up being. Well, if you recall, this base and exponent and this base of exponent could be written differently. They could be written in their factored form. And we might note that x squared is the same as x times x. And we might note that x to the 3rd power is x times x times x. If I have this first group that ends up multiplying by the second group, this really just becomes a string of 5 x's multiplied together. And we see that the end result here is simply x, that base, raised to the 5th power, because there are 5 x's that multiply together. So the power rule states that if we have two like bases, and those bases are multiplied together, then we can simplify the result by adding the exponents. So I'll write this as x to the power of 2 plus 3. And that's where our answer of x to the 5th came from. That's our power rule. Our quotient rule is remarkably similar. Let's start with a different set of problems, and this time I'm going to use a different letter for the base. We'll call it y to the 6th power, and we'll divide that by y to the 2nd power. Well, another way that we can write a division problem is to think of it as a fraction, y to the 6th over y to the 2nd power. And then again, if we think of this as y to the 6th divided by y to the 2nd, we might imagine that the exponent on the top, written in factored form, would require 6 of these y values to be multiplied together. And then in the denominator, we might have 2 of the y values multiplied together. Well, what are we allowed to do if we've got repeated multiplication in the top and the bottom, where some of those factors are exactly the same? Hopefully you recall that if we are separated by multiplication signs between the numerator and the denominator, then like factors can cancel out and reduce themselves. In this case, if I had a pair of y's cancel in this position and in this position, that leaves me with a total of 4 y's, or in other words, y reported as the 4th power. So what would the shortcut have been? If we had started with y to the 6th divided by y to the 2nd, what do we do with those exponents when the bases are alike and they divide one another? Well, the result ends up being a subtraction of those two exponent values, and that's where we get y to the 4th power. So there's an example of our quotient rule. So our next example is the power to a power rule. This one takes an exponent and raises it to another exponent. So the base of our exponent is going to have a base and an exponent itself. We might call this z to the 5th power. So there's our base. That base is being raised to a power of, let's say, 3. So in exponential form or factored form, we might take this base, this z to the 5th power that's acting as our base. We're going to take z to the 5th power and multiply it by another z to the 5th power, and z to the 5th power one more time. This way we've got 3 multiples, or 3 factors of z to the 5th, and if we utilize our product rule from before, we know that we can actually add the exponents together for 2 of these adjacent exponents. So we might call this pair as a combination z to the 10th power, and then we'll multiply that by z to the 5th power, which is going to leave us with another multiplication or product rule, and we end up with z to the 15th power at the end. Now what's the shortcut to take z to the 5th raised to the 3rd power down to z to the 15th power? Well, if you noticed it, good for you. The power rule, power to a power rule states that if I have one power raised to another, then we can actually multiply those exponents together. And z to the 5 times 3 power, or z to the 15th power, is the result when we apply the power to a power rule. So a real quick summary so far, the power rule says that when the bases are the same, we add exponents. The quotient rule said that when the bases are the same, we subtract exponents. And for the power to a power rule, well, we only have technically one letter used as the base, but the base raised from one power to another power, that says that we actually multiply the exponents together. And that's the shortcut. To finish out the video, let's talk about the last two, and these are just general rules to live by. We could talk a little bit more about the where these rules come from and what's the reasoning why they work. But I'll just share those with you, and like I said, we can talk about those more in class. The zero power rule says that regardless of what the base is, let's say that n is our base, if I raise it to the power of 0, the end result ends up being 1. So regardless of the base, it can be any number, any numerical value, any expression. If I've got a base raised to an exponent of 0, the end result ends up being 1. And for our last rule, we have what's called our negative power rule. And some students are not a fan of this because when I first introduce it, you'll see how this negative power rule creates fractions for us to use. And I know that some students aren't really a big fan of utilizing fractions. But in an extension to this rule, we can actually use this negative power rule to eliminate fractions as well. So if I've got m to the negative 5th power, this is going to be the same as m to the 5th power. We can just change it to a positive number if we put it in the bottom of a fraction. So the zero power rule, as a summary, turns everything into 1. Maybe I'll say that it reduces to 1. And then for our negative power rule, I'm just going to make a note that it flips or flipped the fraction. If we think of an exponent as a counter, if it tells us how many times we multiply something together, to me it doesn't make a whole lot of sense to say that we would like to multiply m times itself 5 times in a row. Instead, I would like to divide maybe m 5 times in a row, because division is the opposite of multiplication and addition is the opposite of subtraction. So if you think of it that way, you might see that 1 being kind of our placeholder here, it's an implied initial position. If we start with the number 1 and I repeatedly divide by m, if I took the number 1 and divided by m 5 times in a row, it would actually look like this. It would be the same as multiplying m 5 times in a row in the bottom of a fraction, in the denominator of a fraction. So there's the rules. The law of exponents does have some additional components to it, but here's the first 5 pieces that I think we're going to find most helpful in this class. The beginning of our homework for this week in Math Excel will require you to combine several like bases with one another, and I'm going to give you some time in class the very first day to work through that and to ask for help as needed for clarification. If you have any other concerns or questions, please reach out to me. I'll be happy to help. Thanks for watching.